created by MindSticks Foundation Trust.
Welcome, students, to today's explainer. We are going to break down coordinate geometry step by step. Our agenda today covers the basics of coordinate distance, the distance formula, checking for collinear points, identifying geometric shapes, and finally, some advanced distance problems. Let's dive right in.
Section 1. Basics of coordinate distance. Let's start by refreshing what we already know, all right? Before we jump into 2 dimensions, we absolutely must have our foundation in 1 dimension perfectly clear. Think about a simple number line. Finding the distance between any 2 points is, honestly, quite simple. Take points Q and R, for example. Q is sitting at -5, and R is at 4. To find the exact distance between them, we simply subtract the smaller coordinate from the larger one. So we calculate 4 minus -5. That just becomes 4 plus 5, giving us a total distance of 9. It's very straightforward, it's logical, and it forms the bedrock for everything we are about to do next.
Now, I want you to notice how this exact same logic beautifully applies when we upgrade to a 2D plane. If we have a line segment that is perfectly parallel to either the x-axis or the y-axis, we just repeat exactly what we did on the number line. For points horizontally aligned on the x-axis, we just subtract the x-coordinates, finding x2 minus x1. And for points vertically aligned on the y-axis, it's simply y2 minus y1. You see, the plane itself might look a bit more complex, but the underlying mathematics hasn't changed one bit.
Section 2. The distance formula. So we know how to find distances straight along an axis. But what about a diagonal line segment, like AB here? We can't just subtract the coordinates anymore, can we? But watch this. By dropping perpendicular lines from our 2 points straight down to the x and y axes, we beautifully form a right-angled triangle. Do you see triangle ABC taking shape there? Creating this triangle is a real masterstroke because it allows us to use a very famous mathematical theorem that I know you all remember.
Let's think through the logic step by step. Step 1, we find the horizontal base distance of our newly formed triangle. As we saw earlier, that's simply x2 minus x1. Step 2, we find the vertical height, which is y2 minus y1. And finally, step 3, we take those horizontal and vertical distances and substitute them straight into the Pythagoras theorem. That gives us the length of the hypotenuse, which is the actual diagonal distance we are trying to calculate.
And this step-by-step logic gives us the famous distance formula. The distance AB is equal to the square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. Now, I really want you to remember this. This formula is not magic. It's not just some random string of letters you need to blindly memorize for an exam. It is literally just the Pythagoras theorem working its mathematical wonders on a graph. Once that clicks in your mind, you'll never forget it.
Section 3. Checking for collinear points.
Now that we have our formula properly established, let's use it as a tool to solve some geometric mysteries. Let's start with the concept of collinearity. If I give you 3 completely random points on a graph, let's call them A, B, and C, how can you mathematically prove they sit on the exact same straight line? Just looking at a drawing isn't enough in geometry. We need solid, undeniable mathematical proof.
The mathematical logic here is absolutely clear. If the sum of the distances of the 2 smaller line segments is exactly equal to the largest segment, well, the points must be collinear. Meaning, if distance AB plus distance BC perfectly equals the total overall distance AC, they fall on a perfectly straight line. If that sum is even a tiny bit larger, it means they bend and form a triangle instead.
Walking through this solved example, we just apply our distance formula 3 separate times. We calculate the distance of AB to be 4 root 2. The distance of BC comes out to 8 root 2. And that longest distance AC is 12 root 2. We can clearly see that adding 4 root 2 and 8 root 2 perfectly equals 12 root 2. So because AB plus BC equals AC, we have mathematically proven, without a shadow of a doubt, that points A, B, and C are in a line.
Section 4. Identifying geometric shapes.
Let's see how these distance calculations help us identify specific geometric figures. We often get asked to prove whether 4 given points form a square or a rhombus. Now, both of these shapes have 4 equal sides, right? So to mathematically prove a shape is definitely a square and not just a rhombus, calculating 4 equal sides simply isn't enough. You have to go one step further. You absolutely must prove that the 2 diagonals stretching across the middle are also exactly equal in length.
Taking a look at figure 5.9 from our textbook, we apply the distance formula a total of 6 times. We do it 4 times for the outer sides, AB, BC, CD, and DA, and we find they are all root 34. Perfect. But then we do it 2 more times for the diagonals, AC and BD, discovering they are both root 68. Because all 4 sides are equal and both diagonals are equal, we've definitively proven that quadrilateral ABC is indeed a square. This is exactly how thorough we must be.
Section 5. Advanced Distance Problems.
Before we wrap up today's class, let's tackle a slightly more advanced application. Let's look at a classic problem type, finding equidistant points. This just means points that are located at exactly the same distance from other given points. When asked to find a point on the y-axis that is equidistant from 2 other given points, say M and N, we must first set up our coordinates logically. Any point on the y-axis always has an x-coordinate of 0. So we call our mystery point P, 0, y. We then set up a simple algebraic equation by stating distance Pm equals distance Pn. And here's a pro tip to make the math much easier. Just square both sides. That completely removes those tricky square roots. Then we just expand the brackets and carefully solve the resulting equation to find our y value.
Now check out how this exact same equidistant concept is beautifully applied to find the circumcenter of a triangle. The circumcenter is a very special center point that is mathematically equidistant from all 3 vertices of the triangle, points A, B, and C. By setting up equations where PA squared equals PB squared and PA squared equals PC squared, we can solve 2 simultaneous equations to find the exact coordinates of the center point. It is such a brilliant, elegant application of the simple distance formula we just learned.
So far, we've completely mastered calculating total distances and finding exact equidistant points. But I want to leave you with a real puzzle to ponder. What if a new point breaks a line segment into a specific mathematical ratio, say a 3:5 ratio, rather than just cutting it exactly in half? How on earth would we find the coordinates of that specific point?
This intriguing question brings us to the concept of the division of a line segment, where our point P is dividing segment AB in a 3:5 ratio. To solve problems like this, our distance formula alone won't cut it. We'll need a brand new mathematical tool. Next time, in our next explainer, we will uncover exactly how to conquer this when we learn the powerful section formula. So until then, keep practicing your distance formulas and ask yourself, what other hidden secrets does the coordinate plane hold?